NENOMATICA, where mathematics meets YouTube excellence. Welcome! In today's video, we're going to solve an interesting equation involving factorials and exponentials. Let's look at this equation. N factorial plus 3 equals 3 raised to the power of n minus 1. We need to find how many solutions this equation has in the set of natural numbers. Let's try some specific values to see if they satisfy our equation. Let's start with n equals 1. When we substitute n equals 1 into the left side, we get 1 factorial plus 3. 1 factorial is just 1, so we have 1 plus 3, which equals 4. For the right side, we have 3 raised to the power of 1 minus 1, which is 3 to the power of 0, and that equals 1. So we have 4 equals 1, which is clearly false. So n equals 1 is not a solution. Let's try n equals 2. For the left side, we have 2 factorial plus 3. 2 factorial is 2 times 1, which is 2. So we have 2 plus 3, which equals 5. For the right side, we have 3 raised to the power of 2 minus 1, which is 3 to the power of 1, and that equals 3. So we have 5 equals 3, which is false. So n equals 2 is not a solution either. Let's continue with n equals 3. For the left side, we have 3 factorial plus 3. 3 factorial is 3 times 2 times 1, which is 6. So we have 6 plus 3, which equals 9. For the right side, we have 3 raised to the power of 3 minus 1, which is 3 squared, and that equals 9. So we have 9 equals 9, which is true. So n equals 3 is a solution. Now, let's try n equals 4. For the left side, we have 4 factorial plus 3. 4 factorial is 4 times 3 times 2 times 1, which is 24. So we have 24 plus 3, which equals 27. For the right side, we have 3 raised to the power of 4 minus 1, which is 3 cubed, and that equals 27. So we have 27 equals 27, which is true. So n equals 4 is also a solution. Let's check n equals 5. For the left side, we have 5 factorial plus 3. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So we have 120 plus 3, which equals 123. For the right side, we have 3 raised to the power of 5 minus 1, which is 3 to the 4th power, and that equals 81. So we have 123 equals 81, which is false. So n equals 5 is not a solution. Let's analyze why we don't get any more solutions after n equals 4. We need to compare the growth rates of n factorial and 3 raised to the power of n minus 1. The factorial function grows much faster than exponential functions for larger values of n. For n greater than or equal to 6, we can see that n factorial will always be much larger than 3 raised to the power of n minus 1, plus 3 will be even larger, so the equation won't be satisfied. We can also prove this mathematically. For n greater than or equal to 6, n factorial is divisible by 9, but 3 is not divisible by 9. So n factorial plus 3 cannot be divisible by 9. However, for n greater than or equal to 6, 3 raised to the power of n minus 1 is always divisible by 9 because n minus 1 is at least 5, and 3 to the power of 2 equals 9. Therefore, for n greater than or equal to 6, the left side of our equation is never divisible by 9, while the right side always is, so they can never be equal. Let's summarize our findings. We found that n equals 3 and n equals 4 are solutions to the equation. We also found that n equals 1, n equals 2, and n equals 5 are not solutions. And we proved that there are no more solutions for n greater than or equal to 6. Therefore, the equation n factorial plus 3 equals 3 raised to the power of n minus 1 has exactly 2 solutions in the set of natural numbers. Welcome to our math video. Today, we'll be solving a problem involving exponents, floor functions, and square roots. Let's take a look at our example problem. Assume that it equals 10 to the power of 2 times 1,376 minus 10 to the power of 1,376 plus 1. We need to find the value of floor of 2 times the square root of a. Let me explain what the floor function means. The floor function, denoted by these square brackets with a flat bottom, gives the greatest integer less than or equal to a number. For example, the floor of 3.5 is 3, and the floor of negative 2.7 is negative 3. Now, let's observe an important note in the problem. Notice that we're told that it is between parenthesis 10 to the power of 1,376 minus 1 over 2 squared and 10 to the power of 1,376 squared. This note gives us bounds for the value of x, which will be useful in our solution. Let's begin solving this problem step by step. First, we'll use the note to establish bounds for 2 times the square root of a. From the given note, we have that a is between the square of 10 to the power of 1,376 minus 1/2 and the square of 10 to the power of 1,376. Taking the square root of each part of the inequality, we get that the square root of a is between 10 to the power of 1,376 minus 1/2 and 10 to the power of 1,376. Simplifying the expression under the square root, we get that the square root of a is between 10 to the power of 1,376 minus 1/2 and 10 to the power of 1,376. Multiplying all parts of the inequality by 2, we get that 2 times the square root of a is between 2 times 10 to the power of 1,376 minus 1 and 2 times 10 to the power of 1,376. Simplifying, we get that 2 times the square root of a is between 2 times 10 to the power of 1,376 minus 1 and 2 times 10 to the power of 1,376. Now, we can write this as 2 times 10 to the power of 1,376 minus 1 is less than 2 times the square root of a, which is less than 2 times 10 to the power of 1,376. Therefore, the floor of 2 times the square root of it equals 2 times 10 to the power of 1,376 minus 1. So our answer is 2 times 10 to the power of 1,376 minus 1. Let's summarize what we've learned in this problem. We started with a complex expression involving very large exponents. We used the bounds provided in the note to establish inequalities for a. We then took the square root of each part of the inequality to find bounds for the square root of a. Next, we multiplied by 2 to find bounds for 2 times the square root of a. Finally, we applied the definition of the floor function to determine the exact value. This problem demonstrates the power of using bounds and properties of floor functions to solve problems involving very large numbers without having to compute them explicitly. Welcome to this mathematical exploration video. Today, we're going to solve an interesting problem involving a number with many repeating digits and find the sum of digits of its square. Let's start with our problem. We have a number a, which consists of 81 nines in a row. We need to find the sum of digits of a squared. Let's break this down step by step. First, we need to understand what this number a actually is. A number consisting of n consecutive nines can be expressed as 10 to the power of n minus 1. So for our number a with 81 nines, we can write it as 10 to the power of 81 minus 1. Now, we need to square this number. We can use the formula for the square of a difference. The square of a minus b equals a squared minus 2ab plus b squared. In our case, we have 10 to the power of 81 minus 1, all squared. When we expand this, we get 10 to the power of 162 minus 2 times 10 to the power of 81 plus 1. Now, let's analyze what this expression means in terms of actual digits. 10 to the power of 162 is a 1 followed by 162 zeros. When we subtract 2 times 10 to the power of 81, we get 89s, followed by an 8, followed by 80 zeros, and finally a 1 at the end. This is our a squared in decimal form. Finally, we need to find the sum of all these digits. We have 89s, which gives us 9 times 80. Then we have 1 8 and 1 1. So the sum is 9 times 80 plus 8 plus 1, which equals 729. So the sum of digits of a squared is 729. Let's summarize what we've learned. We started with a number a consisting of 81 nines. We expressed it as 10 to the power of 81 minus 1. We then squared this number to get 10 to the power of 162 minus 2 times 10 to the power of 81 62 minus 2 times 10 to the power of 81 plus 1. This expanded to a number with 89s, followed by an 8, 80 zeros, and a 1. Finally, we calculated the sum of these digits to be 729. Welcome to our astronomy mathematics video. Today, we're going to solve a problem about calculating the average mass of celestial objects in a newly discovered planetary system. Let's begin by understanding the problem statement. Scientists have discovered a planetary system in the Milky Way galaxy that contains 1 star, 9 planets, and 122 moons. Each planet has at least 1 moon. Research shows that the mass of the star is 1.98 times 10 to the power of 30 kilograms. The total mass of all planets equals the mass of the star, and the total mass of each planet's moons equals the mass of that planet. What is the average mass of all objects in this planetary system? Let's organize what we know. We have 1 star, 9 planets, and 122 moons. In total, that's 1 plus 9 plus 122, which gives us 132 celestial objects. The star's mass is 1.98 times 10 to the power of 30 kilograms. We're told that the total mass of all planets equals the star's mass, and each planet's moons have a total mass equal to that planet's mass. Now, let's think about how to find the average mass. The average mass is the total mass divided by the number of objects. To find the total mass, we need to sum up the masses of all the celestial objects, the star, all the planets, and all the moons. Let's use the relationships we've been given to express this total mass. Let's use the relationships we know to calculate the total mass. First, we know that the total mass of all planets equals the mass of the star. So, the mass of all planets is 1.98 times 10 to the power of 30 kilograms. Next, we know that for each planet, the total mass of its moons equals the mass of that planet. Since we have 9 planets, and the total mass of all planets is 1.98 times 10 to the power of 30 kilograms, this means the total mass of all moons equals the total mass of all planets, which is 1.98 times 10 to the power of 30 kilograms. Therefore, the total mass in the system is the star mass plus the planet's mass plus the moon's mass, which is 3 times 1.98 times 10 to the power of 30 kilograms. Now that we have the total mass and the number of objects, we can calculate the average mass. The average mass equals the total mass divided by the number of objects. So that's 5.94 times 10 to the power of 30 kilograms divided by 132 objects. When we calculate this, we get 4.5 times 10 to the power of 28 kilograms as the average mass of each celestial object in this planetary system. Let's verify this result with the given choices. The choices are A. 1.5 times 10 to the power of 28 kilograms, B. 4.5 times 10 to the power of 28 kilograms, C. 6.6 times 10 to the power of 28 kilograms, D. 5.94 times 10 to the power of 28 kilograms, E. Not enough information. Our calculated average mass is 4.5 times 10 to the power of 28 kilograms, which corresponds to answer choice B. Welcome to this math video, where we'll solve a system of natural number relationships. Let's start with our problem. We need to find how many sets of natural numbers A, B, C, and D satisfy the following 4 relationships. The problem gives us a hint. If any one of A, B, C, or D equals 1, then all numbers must be 1, and this gives us one solution. So now we're looking for other solutions where none of the values equal 1. Let's assume that all these numbers are greater than 1. A key insight is to multiply all 4 equations together from the original relationships. A to the power of B equals CD, B to the power of C equals D, AC to the power of D equals ABD to the power of A equals BC. When we multiply the left sides, we get A to the power of B times B to the power of C times C to the power of D times D to the power of A. And when we multiply the right sides, we get CD times DA times AB times BC. Let's simplify the left side. We get A to the power of B times B to the power of C times C to the power of D times D to the power of A. And for the right side, we can rearrange the factors, CD times D, A times AB times BC, which simplifies to a squared B squared, C squared, D squared. So we now have the equation A to the power of B times B to the power of C times C to the power of D times D to the power of A equals a squared, B squared, C squared, D squared. Now, since we assumed all numbers are greater than or equal to 2, we know that A to the power of B times B to the power of C times C to the power of D times D to the power of A is greater than or equal to a squared times B squared times C squared times D squared. This means we must have equality, which can only happen when A equals B equals C equals D. Let's call this common value x. Then our original relationships become x to the power of x equals x times x, or x to the power of x equals x squared. So we need to solve x to the power of x equals x squared. We can take the logarithm of both sides. X times log x equals 2 times log x, simplifying x times log x minus 2 times log x equals 0. X minus 2 times log x equals 0. This gives us two possible solutions. Either x minus 2 equals 0, so x equals 2, or log x equals 0, which means x equals 1. But we already know the solution when x equals 1. Let's check x equals 2. If A, B, C, and D all equal 2, then 2 to the power of 2 equals 4, and 2 times 2 equals 4. White-heady check mark. So this works. In conclusion, we have two solutions. 1. When A equals B equals C equals D equals 1, 2. When A equals B equals C equals D equals 2, therefore, there are two possible sets of natural numbers that satisfy all the given relationships. Let's summarize what we've learned. We had a system of 4 equations with natural numbers A, B, C, and D. We found that there are exactly two solutions, either all variables equal 1 or all variables equal 2. We used key mathematical techniques, including multiplying equations to find patterns, using logarithm properties to solve exponential equations, understanding when equality occurs and inequalities for practice, try creating similar systems of equations, and see if you can find patterns in the solutions. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.